going to be going over a solution procedure for the second problem on exam 2 for EML 3100 for the spring 2016 semester. Initially, we're given a problem statement that we have a silicon wafer that is just out of a heat treatment process. It doesn't really specify what the process is, but it says that this silicon wafer, indicated here in red, starts out at 250 degrees centigrade, and I've gone ahead and converted that to Kelvin, 523 Kelvin. Separate from the wafer, there exists a cooling structure, which is essentially made from steel, steel structure in blue right here, and then I've indicated that it includes air inside. So both are listed in the problem statement. It also says that this structure does not interact with the surroundings thermally, so I've schematically drawn some insulation around it, and we'll include this in an assumption list later on. Initially, the cooling structure and the air are both at ambient temperature, so approximately 20 degrees centigrade, and in Kelvin, 293. And the air pressure is at ambient as well, 101 kilopascals. So I've labeled this as pre-state 1 because, again, these conditions do play into the analysis, but thermodynamically we're concerned with a beginning state and an end state. So the real beginning state of the problem should be with the wafer being placed inside of the cooling structure, which is alluded to in the problem statement. So this would be our thermodynamic state 1, which is not in thermodynamic equilibrium. We have a hot wafer placed inside of this ambient cooling structure with steel and air and surrounded by insulation. So the only interactions in the problem are going to be happening internally to this insulation. Then after some period of time, I have T approaching infinity. It's going to be a very long period of time before everything inside of this cooling structure and the structure itself reaches some kind of thermal equilibrium. And that's why I've drawn everything in orange here. So the structure, the air, and the silicon wafer will all thermally interact until finally there is no temperature gradient spatially or temporally. Again, thermal equilibrium is obtained, and the silicon temperature, air temperature, and steel structure temperature are all going to be equal to some value, which at this point is unknown and is asked for to be solved in the problem. Additionally, the air pressure is being asked for. In the subsequent sequence, I'll list the assumptions, and one of them needs to be something regarding the process. So once we place this silicon wafer in the box, how do we thermodynamically constrain the process? Are we allowing heat transfer to occur at constant pressure conditions, constant volume conditions, or something else? And so we can make an assumption that we have a rigid cooling structure right off the bat that's sealed. And what this would allow us to do is to say, okay, isobaric or constant pressure process is not the one we're looking for, but rather a constant volume or isochoric process. And I've listed that here. So as we proceed from this non-equilibrium state to a thermal equilibrium state, we can constrain our thermodynamic process as constant volume. And doing so, this allows us to kind of narrow down the list of equations or types of analyses we might use to determine both the temperature and the air pressure at the end of this process. And just as a thought experiment, say the air temperature is cooler after the heat transfer has diminished or is over, we would expect that the air pressure would be a little bit lower than it initially started out. But this is obviously going to be the last part of our analysis, and the air temperature, which is going to be equal to the silicon and the steel temperature, is going to dictate what that final air pressure will be. Recapping some of the assumptions that were discussed previously, we've got perfect insulation surrounding our cooling structure. We're also assuming that the cooling structure is both rigid and sealed, which translates into a closed system at constant volume. We'll also assume that the volume of the silicon wafer is unchanged and is also negligible compared to the volume of air within the cooling structure. values which will be listed in a moment. And also, we're going to neglect thermal expansion effects. So, in tandem with saying the cooling structure is rigid, we're also assuming that it's not affected by these thermal gradients as the silicon wafer is cooled and the steel structure is heated. Finally, we're going to assume that the air can be analyzed as an ideal gas, and this is justified right here. It's initially at 101 kPa, so ambient pressure, and 20 degrees centigrade, or 293 Kelvin. Now, if we compare the saturation temperature of oxygen and or the saturation temperature of nitrogen, which air is composed of both, this temperature far surpasses these saturation temperatures at the same pressure, which signifies that it's in a superheated vapor state. And because it's such a highly superheated vapor, it's not a bad assumption that the air itself behaves or can be analyzed as an ideal gas. Also, it's likely we'll be having to use the heat capacities, and we'll assume that they remain constant during the analysis, and we'll neglect their temperature dependence. The numerical values given in the problem statement are as follows. In state 1, for silicon, we have its initial temperature at 523 Kelvin. The density is also listed at 2,330 kilograms per cubic meter. A blue star is indicated next to any value that is going to be held constant throughout the analysis. The specific heat capacity of silicon is listed as 0.7 kilojoules per kilogram Kelvin. And the volume of the silicon wafer is given as 0.1 liters, or 1 times 10 to the minus 4 cubic meters. For air, its initial temperature is ambient at 20 degrees centigrade, or 293 Kelvin. Its initial pressure is essentially ambient at 101 kPa. Its constant volume heat capacity is given as 0.717 kilojoules per kilogram Kelvin. And the volume of the box is actually given as 200 liters, or 0.2 cubic meters, and I've assigned this as the air volume. And this is because if you compare these two values, we're placing the silicon wafer inside of the box, and if you look at this, this is much smaller. 0.1 liters is much smaller than 200 liters, and we can assume that the volume taken up by the silicon wafer is negligible. So the box volume is essentially the volume that the air takes up because it's in the gas phase that's going to fill the entire box. The steel structure, outer casing, is initially at ambient temperature as well, 293. The mass of the structure is 2 kilograms, and steel has a specific heat capacity of 0.46 kilojoules per kilogram Kelvin. At state 2, the final thermal equilibrium state, we have two unknowns that we're solving for in the problem. We're first going to initially see if we can find the final temperature, which I've defined as T final, or again, equivalent to T air, T steel, and T silicon at state 2. And then we're also asked to find the air pressure at state 2, which is likely going to be a function of the equilibrium temperature of the entire structure. Moving forward with the analysis, we will apply the energy conservation principle, or the first law of thermodynamics, for our closed system, which again consists of the insulation, the steel outer structure, silicon wafer, and the air contained within inside. Here, first off, I've drawn a purple dashed line that really cuts through the insulation, but it's meant to allow us to see what exactly we're analyzing, and also note the fact that there's no arrows crossing this boundary. So there's no energetic interaction between the system and the surroundings, or no heat transfer between the system and surroundings. If you can see, there's green arrows I've drawn inside to signify that there are thermal interactions between, say, the silicon wafer and the surrounding air, between the air and the steel structure, and between the steel structure and the silicon wafer. But based on the way we've drawn our control volume, none of those interactions really matter. All we're concerned with is the energy content within the control volume at, say, states 1 and 2, and we'll get to that. Also, I'd like to make a note. I've kind of skipped over mass conservation. It's pretty trivial in the case of a closed system, primarily due to the fact that all the masses stay constant. So we can take them as constants throughout the rest of the analysis. So I've written down here the differential form of the first law of thermodynamics for a closed system. The differential change in internal energy of the system is actually equal to a differential change in heat added or taken away from the system, plus a differential change in work. But as you can see, I've crossed out both terms here. The heat transfer one we've covered a minute ago, primarily because of the insulation and the way we've drawn the control volume. And then there's no work because we've assumed the structure to be rigid. The gas inside actually cannot do any work on the surroundings and vice versa because of the rigidity of the structure. So no boundary work, no pressure work. Also, we don't have, say, a compressor or a turbine interacting with our system, so there's no shaft work, something else we're considering in this course. So really, this simplifies to the differential change in internal energy of the system is equal to 0. So the energy is conserved as we move from state 1 to state 2. We can go down and further expand our expression for U system by accounting for the 3 substances or items within the system that make it a composite thermodynamic system. So really I've just expanded the U, brought this differential outside, and first we've got, say, the mass of silicon times the specific internal energy of silicon, plus the mass of steel times the specific internal energy of steel, plus the mass of air times the specific internal energy of air. And I'm able to break up the terms of U system like this because it's an extensive property and energy is additive. We can go through and actually using these equations over here, which you've seen before, differential change in internal energy for an ideal gas can be related to a differential change in that gas's temperature through the specific heat constant at constant volume. And then also for a condensed phase, say liquids or solids, and we're dealing with steel, a solid steel structure, and a solid silicon wafer in this example, we can relate the change in internal energy to a change in temperature just by C, so a heat capacity. So we don't discriminate between constant pressure and constant volume when it comes to condensed phases. So keeping those in mind, we can come and actually begin to simplify this equation to some extent. This blows up after we differentiate it and then integrate between state 1 and state 2 into this expression on the bottom line here. So the first one represents the mass of silicon times C delta T, essentially. So C of silicon times the final temperature of the entire cooling structure, T final, minus the initial temperature of silicon, that's our first term, plus the mass of steel times the specific heat of steel times the final temperature, same variable, minus the initial steel temperature, plus the mass of air times the difference between the final temperature of the entire cooling structure and the initial temperature of air. And the sum of all 3 of these terms is equal to 0. One further note is that for the mass of silicon, I had to extract the mass from the variables that were given in the problem statement. We were given both the density of silicon and the volume of the silicon wafer. And the product of density and total volume gives me mass. For the air, on the other hand, we initially made the assumption that because it was a highly superheated vapor consisting of oxygen and nitrogen, we could assume that it was an ideal gas and that at any state the ideal gas equation applies. Therefore, to solve for the mass of air, since I don't know the temperature at the final state, I can actually just use quantities that are known at the initial state, so P1 and T1, and rearrange the ideal gas equation of state in order to extract the mass of air, which stays constant throughout the analysis. To complete the analysis, we perform an algebraic manipulation of the 3-term expression that was equal to 0. We finally get T final as a function of all of the variables that were provided in the problem or solved for along the way. This expression for T final looks very similar to the final expression in problem 1 of this same exam. please refer to that video if you haven't seen it already. The three expressions include, or actually look like, combined some kind of weighted average between the three initial temperatures. So the silicon wafer initial temperature, the steel structure initial temperature, and the air initial temperature. And the quantities in brackets are the weighting factors and represent the relative thermal capacities or thermal inertias of those components of the composite thermodynamic system. For example, the numerator of this first term is the mass of the silicon wafer times its specific heat capacity, which gives us units of joules per Kelvin and signifies the amount of energy necessary to raise the temperature of the silicon wafer by 1 Kelvin. The denominator of each of the terms in brackets is the combined thermal inertia of the composite system, so the product of the mass and heat capacity of each constituent. So each of these terms and their temperatures are present here, and after plugging everything in, we get a temperature of approximately 323 Kelvin, which lies in between the minimum temperature, which was ambient, or 293 Kelvin, for both the steel structure and the air temperature, and the maximum temperature of the problem, which was about 523 Kelvin. And again, because it lies between the minimum and maximum temperatures, the second law has not been violated, and thus this provides us with a sanity check for the algebra and the problem. If we move on to the second part of the problem, it asks us what the final air pressure was. If we look at this air temperature, again, the structure, the wafer, and the air are all at the same temperature once everything has come to equilibrium. This temperature, 323, is higher than the initial 293 of the air, so the air's energy has increased to some extent, and we would expect its pressure to go up. And we can verify this by simply applying the ideal gas equation of state at state 2. We already know the mass of air, which hasn't changed throughout the process. The specific gas constant for air, this is a constant. T final, again, solved for above. And the volume of air also stays fixed. We constrained our thermodynamic process to be isochoric, or constant volume. So plugging in values, we could initially found that I think from a previous part of the problem, that the air mass was 0.24 kg. The specific gas constant for air is nothing more than a ratio between the universal gas constant and the molecular weight, and that gives us 287 joules per kilogram per Kelvin. Plugging in the final air temperature of 323 Kelvin, and then finally dividing by the air volume inside the container of 200 liters or 0.2 cubic meters. And this gives us an air pressure at state 2 of approximately 111 kPa. And this is about 10 kilopascals higher than the initial air pressure, and is consistent with what we thought would occur since the air is now at higher energy level. And hence the pressure is higher, signifying a little bit more momentum transfer to the walls.
The Teaching Center, UF's Learning Resource Center.